Hi, pre-calculus. We are looking at section 6.2, and we're going to be talking about linear and angular velocity. Our first vocabulary term is angular displacement, and angular displacement really refers to the idea of traveling kind of along a circle. Let me get a circle up here real quick. Traveling along a circle. So if you have some object traveling along a circle, and at one time the object is, say, here, and then later on the object is here, then the angle with which that object has traveled, let's call it theta, would be the angular displacement. So it's how far in terms of the angle, not in terms of the length, right? But in terms of the angle. So if I were to have, let's say, a larger circle, and I could talk about another, let me get out of here. If I were to talk about this blue dot that has traveled from here to here, it makes sense that the angular displacement could be the same even though the distance is different. So if these two theta values are equivalent, then our angular displacement would be the same. So when we talk about angular displacement, or movement along a circle, we also come up with this concept of an angular velocity. And so the angular velocity, which is given by this Greek letter, which is omega, I'm pretty sure, is omega is equal to the angular displacement that we talked about before, divided by time. So it's, in a sense, how many degrees, let me slide up here, how many degrees this particular object could travel over a certain amount of time. And so that's what angular velocity would be. The idea of dimensional analysis, you've probably seen it before, guys. It's when you are basically changing units from one way to another. So for instance, if I knew that we were traveling at a 45 miles per hour or something like that, then I would use dimensional analysis if I wanted this answer to be in, let's say, feet per second, right? And so you guys kind of remember how that happens. You would change your hours to seconds. So you would have to remember that 1 hour is equal to, I think, 3,600 seconds. Am I making that up? Hopefully I'm not. You know what it is. Okay, so then we would change, so that would change our hours to seconds, and then our miles, we would then recognize that we need 5,280 feet to 1 mile. So after we go through this dimensional analysis, we would get our answer in feet per second. And so that's what that is. And hopefully you remember what linear velocity is from maybe a science class or just, regular language. Linear velocity is basically just distance divided by time. So your linear velocity is very close to the idea of speed. So one little caveat we want to keep in mind is that in our text, we are using S for distance traveled. And so you remember when we were dealing last section with considering like the distance that an object or something would travel in terms of the pizza crust or the length of of this arc here, we could determine that length. We would say that length S is equal to R times theta. And so if we were trying to figure out the velocity, the linear velocity of an object in a circle, we would have to use this idea. So the linear velocity would be R times theta over T. And so that's something that we will use a little bit later on with our problems. Example 1 asks us to determine the angular displacement in radians of a 4.5 revolutions, and we're going to round to the nearest tenth. So let's just kind of have a visual on this. If we start off at a circle and we are considering an object that goes around 4.5 times, right? We're trying to figure out what the angular displacement is. So what is that angle measure? What is the angle measure of 4.5 revolutions? So considering that one revolution, we know that one revolution is going to be equal to 2 pi, right? If we're dealing with radians, then we can take that 4.5 and multiply it by 2 pi, use a calculator, and the answer that we get is approximately 28.3 radians. In this example, we're going to be determining the angular velocity of 7.3 revolutions are completed in 5 seconds. Okay, so if you have, and we're going to round to the nearest tenth. So what is angular velocity again? We use omega. That looks really not like the omega, something like that. Omega is equal to theta over t. So we need to figure out the, basically we know that theta is going to be the angular displacement. We need to figure out the angular displacement. Well, we just did that in the last problem where we take the 7.3, we multiply it by not 2 point anything, but 2 pi, and then we're going to divide that by 5. And so with the calculator again, we're going to get our answer of 9.2 radians per second. So here in example 3, we're looking at some information that we saw at the beginning of the chapter. And here we have a diagram of what amounts to be a carousel ride that's at the Children's Museum in Indianapolis, Indiana. And what we know is that from the center of the carousel to the first like inner circle of, I guess, animals, horses, whatever that they have that you can ride on, that distance is going to be 11 feet, and then the distance from the center to the most outer edge is going to be 20 feet. And so what we're being asked to do is to determine, in this first one, let's look here, we're going to determine the angular velocity for each rider. And what are the riders? So there's one person here at the 11-foot mark, and then there's one person who is kind of in the same row at the 20-foot mark. So 11 feet, 20 feet. And so if they go around 2 5/8 rotation per minute, we want to know, well, if they go around 2 5/8 rotations, we want to know what their angular velocity is. And so we remember angular velocity, that's going to be omega, is equal to theta divided by t. And so this theta value, of course, we know is angular displacement. And what we also know is with these revolutions that the riders are going around, their theta value or their angular displacement is going to be the same for both of them, right? It has to be the same if you're thinking about it in terms of the example we talked about when we were discussing vocabulary. So with that in mind, let's get to that angular displacement, which is going to be 2 5/8 times 2 pi. And then we're going to divide that by the time. It says that the carousel makes these rotations per minute. So 1 minute would be 60 seconds. Because let's do it in radians per second. And then so with our calculator, we get the angular velocity of 0.275 radians per second. So here, for example 4, we're going to determine the linear velocity of a point rotating at an angular velocity of 17 pi radians per second as at a distance of 5 centimeters from the center of the rotating object. And we're going to round this answer to the nearest tenth. So here's what we remember. We're looking at linear velocity. We know that linear velocity in our text would be considered the distance divided by the time, but we know that this distance that we are talking about, an object traveling in a circular path, is going to be r times theta. So our linear velocity would be the radius times theta, which we know to be the angular displacement over t. And so we're going to use this formula to answer the question. So let's see what we can do. So the radius we have given as 5 centimeters, and the angular displacement is 17 radians per second. And that's going to give us two things: the angular displacement, 17 pi radians per second, over the time, 1 second. And so if we just multiply these guys together, we should be able to get the value we're looking for, which is 267, or approximately 267 centimeters per second. So looking back at the same example that we talked about in section 3 when we had our carousel and we were considering angular the angular displacement, right now what we're going to consider is the linear velocity. And so remember, linear velocity requires a couple things. When we're dealing with linear velocity, we're talking about the movement or the distance moved over time. When we're talking about it along a circular path, that's going to be r times theta over t. So what we need to do, r being the radius times theta being the angular displacement over the time t. So we have a couple bits of this information that we have already. We have it at our disposal. So let's go ahead and work it out. So I'm going to first do it for the person who is at 20 feet away from the center. So I'll highlight that in purple and I will keep on going. So we're going to write this as 20 times theta, which is the angular displacement, which we know to be 2 5/8. That's the revolution times 2 pi, which is the angular displacement of one complete revolution. And then I'm going to divide that by time, which is 60 minutes. And just because I'm working on that, now I want to, in one fell swoop, do the other one as well. So for the, there we go, for the 11, the person 11 feet from the center, we would just have this as 11 times 2 5/8 times 2 pi, again, over 60. So we're doing this not per minute, but per second. And so with our calculator, we get for the person sitting 20 feet away from the center, we get 5.5 feet. And for the person sitting 11 feet from the center, we get 3.25 feet. Make sense? Hopefully that makes sense. All right, let me see if I can change that color because that color was a little bit off. It should be purple. Well, whatever. You get what I'm trying to say. All right, cool. Let's go ahead and look at the last example. So in the final example, example 6 says that we have the tires of a race car that are 30 inches in diameter, and if the tires are turning at a rate of 2,000 revolutions per minute, determine the race car's speed in miles per hour. So let's kind of think about what we have. We know that the race car has a diameter of 30 inches, and so that implies that the radius is going to be 15 inches. And we know that we've been using a radius in a lot of our formulas, so having radius would be helpful. And then the next thing we need to do is calculate the linear distance that the tire propels the car. So we need to figure out how far is this car going in terms of 2,000 revolutions, right? And so what we would do is we would actually come up with the linear velocity, and that we know to be r times theta over t. And so if we start off with the 15 times theta, theta being not just the 2,000 revolutions, but 2,000 revolutions multiplying that by 2 pi. So we get the angular displacement, and then we're going to divide that by how long it takes for that to happen, which we know is going to be in, they want to know miles per hour. So I'm going to leave it in minutes for now. So this is, I'm going to put this in here as 1 minute with my calculator. Actually, before I get my calculator out, I'm going to set the whole thing up in such a way that we can pull our calculator out only one time. So 15 times 2,000 times 2 pi is going to give me the velocity, not in meters, not in miles per hour, but we're going to get the velocity in feet per minute, right? So this would be feet up here, and this would be 1 minute. So that's feet per minute. But since we want to change everything to miles per hour, we have to use this dimensional analysis that we mentioned before. And you don't have to, but it can be helpful. So let's just go through it right now. So if I want to change the feet to miles, I have to remember that 1 mile is equal to 5,280 feet. And so what I would do with that information is, since I want miles at the top and I want to get rid of the feet, I'm going to put 1 mile over 5,280 feet. Okay, So what that's going to do is cancel out the feet, and then so my answer will now be in miles per minute. But I don't want miles per minute, I want miles per hour. And so I have to remember that 1 hour is equal to 60 minutes. And so how am I going to use this conversion factor? Since I want hours in the denominator, I'm going to put my 1 hour in the bottom, and I'll put my 60 minutes on top. And so now, after I've kind of sorted all of that out, it's much better for me to go grab my calculator, and so I can put all of this information in, and then I can get an answer that is more helpful. Actually, I kind of mistook one thing, and I'm going to fix that before I get to my calculator. This should be in inches. As I started calculating, I realized that's not going to work. So this should be in inches. And what that does is tells me that I've got to change my inches, not into miles, but I first need to change my inches into feet. Then I can change those into miles. So that's going to require me to have one more conversion factor. Stay with me, stay with me. So I'm going to scooch this over just a bit and add another conversion factor in there. So I know that if I have inches, I know that 12 inches will give me 1 foot. And because of that, and I know that I want feet to be in the numerator, so then I could eventually turn those feet into miles, right? I am going to write this as 1 foot over 12 inches. So it, in essence, basically gives me the opportunity to take all those inches divided by 12, then I get feet, take those feet divided by 5,280, and then I get miles. You see what we're doing? I hope that makes sense. I hope this is more review. And if you guys want to talk about it with me, we can talk about it. Let me remove my conversion factors there so I can write my answer down below. So after multiplying everything in the numerator and dividing by everything in the denominator, we get approximately 178.5 miles per hour as the velocity or as the speed of this particular race car. All right, I hope that that was somewhat illuminating or helpful. I look forward to talking to you soon. Please, please take care.